In the world, there's over 4,000 gigawatts of installed fossil fuel capacity out there. And our goal is to replace it all. And I don't think a one type of fusion probably is enough to do all that. We're going to try. We're going to move as fast as we can. But I think that you're going to have different kinds of power in different locations, and you're going to need those, whether it's remote, whether it's military bases, whether it's giant factories, whether it's data centers, and they're going to require different kinds of power. And so our plan is, yes, we demonstrate electrons on the grid in 2028, and then we have to scale and manufacturing as fast as possible and start manufacturing these systems to deploy them. And so we're going to do that as fast as possible. Our goal is to get to, by 2030, we're now making generators, and we're making generators per day rather than generators every few years. That's a big scale. That's a big lift. And so as a human, I want other fusion and other types of advanced carbon-free power out there in the world too, because we just have that big of a need, and we need to move that fast.
The person you just heard from is David Kirtley, the founder and CEO of Helion Energy. The dates David mentioned, 2028 and 2030, are 5 and 7 years away. He believes that Helion Energy will deliver fusion-generated electrons to its first customer in 5 years and to the grid in 7. On the last episode, we talked about the joke that fusion is always 30 years away, but today, that joke is far too pessimistic.
Helion is one of a batch of roughly 80 startups working to make fusion happen within the next decade. In the bizarro relay marathon that is the fusion race, the baton is firmly in the hands of these startups. The outcome, to be sure, is still uncertain, but the question isn't whether humanity will achieve commercial fusion, but which companies will, with what approaches, and when.
This is truly an extraordinary time to be alive. Between solar, fission, and fusion, we're entering a new era in human history. For the first time, we won't primarily produce energy by burning things. We'll be able to manufacture energy by capturing the sun's rays, splitting atoms apart, and fusing them together. Fusion, many believe, will be one of humanity's greatest triumphs. We'll be able to generate energy in the same way that the stars do, right on Earth. And we have one of the coolest jobs in the world because we get to talk to some of the people who are most likely to make it happen.
Today, we'll be talking to 5 fusion founders and operators, each taking a different approach to generating fusion energy. We'll have David Kirtley at Helion Energy, JC Bache at Fuse Energy, Francesco Shortino at Proxima Fusion, and Ryan Umstad and Derek Sutherland at Zap Energy. We'll also hear from a few of the investors we met on the last episode. Clay and Clea at Lower Carbon Capital, who tell us about a few of their portfolio companies like Commonwealth Fusion Systems and Avalanche Energy, and Ian Hogarth at Plural Platforms, who will explain why he's making a concentrated bet on Stellarators.
I have to say, these interviews were one of the coolest parts of doing this series for me personally. Last week, I was reading my son Dev this book on quantum physics because I'm trying to correct, I guess, the lack of physics knowledge that I have. And one of the pages was about fission and fusion. The next night, I had to miss story time for our conversation with David. And when I got off, it was kind of surreal getting to tell Dev, remember fusion, the thing where you smash 2 atoms together to make energy? I just got to talk to one of the people who's actually going to make that happen. This sounds like a made-up Paul Graham, my 3-year-old said this profound thing story, and Dev only kind of cared. But it was one of those moments where it hit me that a lot of the people that we've spoken to this season, including you, have a shot at making the world legitimately better for a lot of people, including our kids. It's why we started Age of Miracles with fission and fusion. We think this stuff really matters. Anyway, we have a lot to cover in this one.
Let's do it. First, we'll answer the question of why now for fusion, and for startups in particular, by talking to the companies taking advantage of the moment. Next, we'll dive into the business models and the economics of a fusion plant. And finally, we'll discuss what a rollout of fusion across the globe might look like. That feels crazy to say. It makes fusion seem almost mundane, like an ordinary business, but it's something that these operators are already thinking about and planning for. If commercial fusion is going to change the world, it needs to be commercially viable. Let's start with one of a venture capital's favorite questions. Why now? Why, after 80 years in government and academic labs, has fusion finally broken into the commercial sector? And why might these companies, which have much smaller teams and smaller budgets than these international government projects, actually make fusion happen first?
Why now is maybe the most important question in Fusion, and there are 4 main categories of answers. 1, government-funded breakthroughs. These startups really are standing on the shoulders of giant research programs. 2 is the funding landscape. With climate change a looming threat, both governments and venture capitalists are willing to back companies that have a shot at contributing to a solution. 3, technological advances. Better materials, better software, better components have been game changers for the startups that we've spoken to. And 4 is startup speed and iteration. Inspired by companies like SpaceX, startups are taking approaches that governments can't or won't to get to market more quickly. Clean Air Task Force's Sahila Gonzalez has been in Fusion for 2 decades, and she told us she's never seen a time as promising as right now.
Well, I have been in Fusion already almost 20 years, and I had never seen the excitement and the hope for the future that I have seen in the last 2, 3, 5 years, okay, from now. Before, Fusion was something done in the academia and in some national labs. Now it's something that is on the Financial Times, The Economist. So I think we are really in a good moment. We have the private capital and the private sector, which is providing flexibility and a more agile approach to Fusion, which is really convenient. We have a lot of knowledge generated in the public sector, in the traditional sector, which is very important because without knowledge, you cannot progress. We have tools that we didn't have before. So all the artificial intelligence, all the new software tools, all the, for example, in terms of superconductors, all the developments, all these new elements that maybe has been created out of Fusion, but help Fusion to progress. We are in a time where tools that were not existing 10 years ago are available now, and more that will come in the next year. So, and together with the need of new source of energy, which has to be clean. So it's a really good combination of having new tools and having the need to have this new source of energies, which are making Fusion to go faster than ever now.
Clay Dumas at Lower Carbon Capital said that he came into his first Fusion pitch skeptical and came out sold because of the very same trends.
Very early on, we were offered an introduction to Bob Mumgard, who's the CEO and co-founder of Commonwealth Fusion Systems, which to many people was kind of the introduction to private fusion companies. And to be totally candid with you guys, the first conversation we went into thinking, like so many other people, that fusion is 30 years away and it always will be. But we got this introduction from someone we really like and respect, and this could be interesting. So let's go in with an open mind. And we came out of a 1-hour conversation with Bob, completely sold, committed to invest in CFS's, it was their Series A, but it was their first round of outside capital because they raised $100 million all at once. But also really curious about different paths towards commercializing fusion technology. One of the big takeaways from the conversation with Bob was that the same trends that were benefiting CFS were not exclusive to CFS. And in fact, they would give rise to other pathways to commercializing fusion. First, you were benefiting from major advances in material science, which had big implications for the kinds of magnets and superconductors that CFS was looking to develop, but which has broad implications, not just within fusion, but with, everything from transmission to cancer research. You were also seeing the impact of really cheap compute and a generation of engineers that were steeped in machine learning and advancing towards something that I think with a straight face, we can all look at each other and say is really AI today. And that had big implications for how we simulate what happens in these super weird plasma conditions. When you reach 150 million degrees Celsius, and you're trying to figure out how these tiny little particles interact with one another. And having greater fidelity of what was happening in those conditions from running models on computers really was speeding up the rate of learning and physical world testing that companies like CFS were really on the cutting edge of.
Each of the startups we spoke with takes advantage of all 4 in some way, so we wanted to flag them up front so you know what to look for throughout the episode. Like Clay, we hope that by hearing from the founders directly, you'll come away with a greater appreciation for how close we might actually be and why. You might even leave this episode with thoughts on which company will get there first. That's one of the fun parts about watching a race. So let's meet the fusion startups and hear why they think now is the right time to build fusion in the way they're building it. While fusion seems like a sci-fi technology, these are real, serious people with real practical plans to bring it online. Their backgrounds and experiences range from years in some of the world's top fusion labs all the way to a simple high school background.
Let's start with the 800-pound gorilla in fusion, Commonwealth Fusion Systems, or CFS. While we didn't get a chance to speak with CEO Bob Mumgaard or Chairman Dennis White, we highly recommend that you listen to Dennis's conversation with Lex Friedman. We'll link to it in the notes and the resources guide. For now, here's Clay to explain what CFS does.
Well, the first and probably best understood fusion reactor design is a tokamak. This is a reactor that's being commercialized now by Commonwealth Fusion Systems outside of Boston. And it's the one that has received the most attention and dollars from researchers over the past 4 to 5 decades. As a consequence, it's the one where the physics are the most de-risked. And it's part of the reason why CFS has been able to raise as much capital as they have in pursuit of a tokamak. One of the downsides for tokamaks historically has been that they have to get really, really big because you need extremely powerful magnets to confine plasma at these outrageous conditions of more than 150 million degrees Celsius, which just for a frame of context is like hotter than the center of the sun. And so for a long time, the kind of leading concept in people's minds who study this of what a tokamak was is ITER, which is this multinational effort to develop a Q greater than 10 reactor in the south of France that's billions of dollars over budget and at this point decades behind schedule. CFS has turned the concept of a tokamak on its head and taking a really large reactor and making it small by shrinking the size of the magnets, but making them much, much more powerful using superconductors. That isn't to say that tokamaks are fully understood. There's still a lot of work that has to be done to keep those reactors operating under safe conditions and keep the reactions themselves continuous and contain the plasma. But there's a reason why CFS is often referred to, not just by itself, but by people in the know as the safest and in some ways surest way to commercial fusion.
CFS is a giant in the space. Spun up out of White's lab at MIT, where Mumgaard was a student, the company has raised $2 billion from investors including Lower Carbon, Bill Gates, Breakthrough Energy, Alphabet, and Coastal Ventures. Like Clay said, it's the safest bet. Tokamaks are well understood, and thanks to advances in magnets, CFS can scale down its reactor, speed up development, and make fusion commercially viable. White is a legend in the field, having worked on ITER before heading to MIT, as you heard in the last episode. CFS expects to bring its first 200 megawatt electric plant online in the early 2030s, and the smart money is betting that they'll do it. But CFS certainly isn't the only startup in the fusion race, and ITER to MIT to startup isn't the only route. J.C. Bache took the most direct and least conventional route into fusion. He skipped college and started building.
Yeah, so growing up, my father was actually a nuclear physicist, so I was fascinated about the universe and how things work, and I really wanted to go see it. And I was very disappointed when my father told me that we've never had a human go and actually physically see the universe, and it's not quite possible. And so I started Googling how can we go to space, and how can a human go to space and come back and tell the world about what they've seen. And so as part of my Googling, I found like the only reasonable possible way to do that is if you build like fusion drives, like fusion powered rockets. And so I started like aggressively reading about, fusion drives, fusion powered rockets, and really wanted to build one. And so this led me to like actually be motivated to sit in the classroom for a little longer in high school, and ended up doing like some research in plasma physics when I was still in high school. And this was my first, more formal exposure to like fusion. But then from there, I realized that for me to learn the fastest, to make the most amount of progress, and to have the biggest impact on the field is much better to build a company rather than, sit in a classroom. So decided to build a company essentially in lieu of going to college.
Perhaps because he hadn't been colored by years of research or experience in a lab, JC approached the fusion space with a fresh sheet of paper when starting Fuse Energy out of Canada and asked the fundamental questions. Starting today, what is the best approach to fusion and one that customers will be willing to buy?
There were a lot of academics at the time that were very convinced, that their research, they've done like very impressive research. It was, great. It was time to spin it out. But I started looking at like where are the governments spending like billions of dollars, because the government are like the most incentivized to make this work. And this led me to find out about the Z machine, which is one of the most successful nuclear experiments in the United States and in the world. It's the highest source of X-ray, has the Guinness World Record of the highest temperature achieved on Earth. And I was like, okay, why is no one building it? This was refurbished in 2007. It was pretty old technology. And it had reached very impressive results, and it's 10 times more efficient than lasers, and it's 10% the cost and the size of NIF, which is like the experiment that achieved ignition for the first time in history, but like no one's paying attention to it. And there's a very clear roadmap that people within the field have laid out for the next generation of the Z machine, but no one was building. And every time you ask, it's like, oh, we know we need to do this, but it's taking time. We're trying to get the approval. And so we just went and built it. And today, I think we've built like the world's first and highest energy pulse power driver ever built. And so we're working to essentially build the next generation of the Z machine or of maglev.
I'm going to break in here to explain. On the last episode, Andrew Cote talked about the Z-Pinch generator design. The Z machine is related, but slightly different. The Z machine is a specific facility located at Sandia National Labs that uses the principles of Z-Pinch as part of its operation to achieve high energy density conditions for research and potential fusion energy production. It's the world's most powerful and efficient laboratory radiation source, using high magnetic fields associated with high electrical currents to produce high temperatures, high pressures, and powerful X-rays for research used in high energy density physics. While Sandia uses the Z machine for things like research on nuclear weapons and validating physics models and simulation, it can also be used to incinerate things and to generate fusion energy. Back to JC.
The reason we chose it is there's three main reasons. So first, objectively, controlled implosion methods lead the race for fusion. Like NIF is the highest result, Z is right after, and there's the tokamaks. So it was a very practical path. There's billions already and decades behind this research. Granted, it's more behind closed doors, but it was very mature. And our value prop was very clear to go to the next generation. The second reason is this is a technology that's very critical. And I think it's very important when you look at building and fusion or any hard tech, truly long-term mission company with a vision that may take like decades to materialize, to pick a technology that actually could be commercializable and like step function, and building capabilities or the technology that would enable us to build the next generation of Z is immediately useful today to respond to multiple like national security needs. And so this was a very important factor. And then the third point is this approach is the only one that actually has an intermediate step towards providing power, which is essentially using the fusion neutrons to bombard radioactive waste and used a hybrid fusion fission concept to produce power along the way. So it's still, it's an idea that there's very polarized opinions, but it's just an option. So these were the three main reasons why we chose to work on what we're working on.
Already in JC's answer, you hear a couple of the why now themes. One, Fuse is building the next generation of a technology, Z machines, initially developed by the government. And two, it's building something that might make sense for government funding and something that customers might be able to buy sooner rather than later.
His idea about the intermediate step is really smart. It's a bit of a fission-fusion hybrid and a perfect bridge between the first half of the season and this one. Before Fuse gets to fusion power, it can use neutrons from a fusion reaction to create a fission reaction from nuclear waste, kind of like a fast breeder reactor.
So traditionally, there's a bunch of radioactive waste that's usually stored after the traditional reactors actually work. And so what we can do is this is essentially decaying for 100,000s of years, right? So what we can do is if we take a fast neutron, right, which is like the fusion neutron that comes from a fusion reaction, so from like a deuterium, like a normal fusion reaction, and we can surround the fusion chamber with actinide, so the radioactive waste, the neutron will actually accelerate the rate of decay of the radioactive waste. So it will excite it in some way, and that will lead it to decay at a much faster rate, which will reduce the half-life from 100,000s of years to like tens of years. And because the radioactive decay is happening faster, it will release more energy. So there's one point, which is just the waste recycling or treating the waste, which today I think it's $40 billion a year, but just in the United States. The original concept was called the incinerator because it's the Z machine. So they call it the incinerator. But also if we end up doing it efficiently, we can be producing power. So we can actually, that could be a synergistic step where we actually can start producing power and be a power generating company. That's separate from just the waste recycling. Now, I think that will take more engineering, but that's a dual use, essentially like revenue or customers.
Thanks for listening so far. Hang on, we'll be right back after a quick word from our sponsors. Age of Miracles is sponsored by my longtime partners and friends at SecureFrame, the only compliance automation platform with AI capabilities that helps customers speed up cloud remediation and security questionnaires. One of the things I love about SecureFrame is that it takes this annoying thing that every company has to do in order to unlock revenue from other companies and makes it easy and simple. SecureFrame empowers businesses to build trust with customers by simplifying information security and compliance through AI and automation, not wasteful human hours. By automating manual tasks related to security, risk, and compliance, SecureFrame allows companies to focus on growing their business, the thing that they're there to do. That's why thousands of fast-growing businesses, including AngelList, Ramp, Remote, and Coda, trust SecureFrame to expedite their compliance journey for security and privacy standards such as SOC 2, ISO 27001, PCI DSS, HIPAA, GDPR, and more. Trust me, if there's an acronym that your company dreads, I bet SecureFrame can help. And I recommend it to all of my portfolio companies. So if you're listening and you don't want to deal with all of those forms and you want to let SecureFrame handle it for you, sign up for a free demo at secureframe.com and mention Age of Miracles during your demo to get 20% off your first year of SecureFrame. This episode of Age of Miracles is brought to you by Tegus, the go-to research destination for bold investing. Investors are always on the lookout for the companies who will disrupt the status quo. So why stick with vendors who are unwilling to innovate? Tegus is opening up a whole new world for investors. It gives you access to new data, proprietary data, AI, and technology that no other company in the world has. With its unified platform, you can combine fragmented workflows under one roof and compete on your ability to analyze companies, not on how well you aggregate data. The impossible is the new normal. Learn more and start your free trial at tegus.com/miracles.
Fuse's path to market involves generating revenue from things that are near-term feasible, like disposing of nuclear waste and producing power from nuclear waste on the path to generating pure fusion energy. Most fusion companies need to build multiple generations of generators on their way to commercial fusion, and JC is betting that he can start generating revenue earlier in that journey. Others are taking different approaches, like Germany's Proxima Fusion, which is taking advantage of another big why now, better simulation software to run as much of its design in silico as possible before ever touching metal. You heard the phrase in silico on the last episode, when we told you about the world's largest stellarator, and the first to be tested in silico before construction, the Wendelstein 7X at the Max Planck Institute in Munich. It's no coincidence you're hearing it again here. Proxima founder and CEO Francesco Shortino worked on W7X before launching Proxima and set up the company's operations nearby.
We are a company based in Munich. We created the company in January 2023, got a team together from 3/4 of the original team is from the Max Planck. And then one of my co-founders is also from MIT. I myself was at MIT with him during my PhD. And then Martin joined us, another one of the co-founders from Google X from California. The company really aims at taking this visionary project that Wendelstein 7X is, so this stellarator in northern Germany, and going the next step, using this simulation-enabled concept, leveraging the high-field superconducting magnets that we can make today and that not so many years ago were just a dream. We can design now solutions to problems that historically in magnetic confinement fusion have been complicated to deal with in experiments. Now we can design the solution from early on, let's say. This idea of translating some of the complexity of tokamaks into a more predictable kind of device, a device that really works like a microwave oven. The idea is you want to turn it on, it should just run steady state, continuous operation with no surprises, no behavior that you cannot really expect. And then you turn it off when you choose to do. That's what we are chasing as a as a company.
Francesco listed a few big why nows for Proxima. 1, building off the Wendelstein 7X and partnering with Max Planck. 2, new materials, specifically high-field superconducting magnets. Stellarators are a form of magnetic confinement fusion like tokamaks, so good magnets are key. And 3, and most importantly for the company, software simulations. Proxima plans to design and simulate the reactor, making trade-offs between physics and engineering in software before they ever touch a piece of metal. Recall that on the last episode, Ian Hogarth, whose Plural Platforms led Proxima's seed round, told us that stellarators were the platonic ideal of fusion generators. But before those advancements, they were just too hard to build. When we asked her to explain stellarators, Lower Carbon's Dr. Clea Kolster made a similar point. She said that stellarators have gone from impossible to imagine building to possible.
So then stellarators is like the, I don't know, maybe you call it like the ugly duckling of the tokamak. Basically, it's a similar concept. It's magnetic fusion energy where you're confining plasma using a very strong magnetic field. But in a tokamak, you have the toroidal magnetic field, and then you have a poloidal magnetic field in the middle, and then a current running through the plasma. The other name of the game with fusion is how do you minimize instabilities in your plasma? And so the like optimization between all of those different magnetic fields and moving pieces is what either drives the instabilities or keeps the instabilities down. Keeping them down is what you want. Stellarators, very twisty, crazy configuration that historically was just impossible to imagine ever being able to build or being able to actually simulate because of how complex it would need to be to know how the plasma would work. Now, today we both have much better computing, so you can actually understand what that very complicated twisting magnetic field looks like and operates like. That's what happened at the German Max Planck Institute, where they have a reactor called W7X. And the stellarator there was the first to show plasma stability within a stellarator. Now, what we found really exciting in the actually 2 companies that are working on stellarators that we've invested in is in their theory of change around making those more simple to build and easier to maintain. On the one hand, potentially through controls or through being able to laser pattern that magnetic field directly onto the material instead of basically having to configure it and make it all at once, which, as you can imagine, is like a manufacturing nightmare. The perceived benefit of this reactor configuration is that because you don't need that additional magnetic field in the middle, the poloidal magnetic field, you could make stellarators way smaller, which also in theory would drive down the cost significantly and would mean that you like altogether would need much less materials to make them.
With better software, Francesco agrees that building stellarators becomes more feasible, and that when you do, you have yourself a powerful source as predictable and easy to operate as a microwave oven. Not being a plasma physicist or fusion engineer myself, I asked him to explain a little more about what makes stellarators ideal.
Just by the concept itself, you don't have pulsed behavior. So every single fusion concept, as far as I am aware, involves some sort of up and down behavior, some form of either implosion or a sudden large amount of energy, or it can be pulses that go over hours. But all fusion concepts involve some sort of great energy input and some great energy output. Stellarators are the only concept that is truly steady state. You can build a stellarator that just runs, as I said, like a microwave oven. This had to be demonstrated. W7X has demonstrated that this is now just done. W7X has been run last year for minutes, and there is nothing happening after 20 seconds or so. So that's one key advantage. The other one is that you are fully controlling your hot ionized matter, this plasma that we have to confine at 150 million degrees. You can confine it completely externally with some big coils. And so the challenge in a stellarator is, can you design these coils? Can you design coils that can go to high enough magnetic fields? Because the fusion power scales with the magnetic field intensity very strongly. So if you can get this cage, this magnetic cage done well, then you start addressing other aspects of the design. You have to support the huge forces. You have to deal with humongous heat fluxes, lots of things. So you need to have a capability in designing and assessing the trade-offs. And that's what is the nature of Proxima Fusion, a group that has these tools and understanding of where do you go and put your effort on the physics questions, on the engineering questions. We are founded on the belief that we are in a transition from a physics focus to an engineering focus with a mindset on commercial viability. And Stellarators, in our opinion, have just a much better market fit. If you are able to deliver continuous base load, much more simple to use kind of device, then you have a much better future. The question is, can you design it? And then can you manufacture it? And if we hadn't seen that W7X was manufactured with incredible achievements on the technical manufacturing tolerances, if we didn't have it, I think it would be a bad idea to go into this because it would be sort of improbable. But we've done it.
This physics and engineering trade-off is one that we've heard come up a few times, not just with Stellarators. It's the core of the approach that Zap Energy is taking. Zap is making a different bet than many of the fusion companies out there. Instead of pushing to the outer limits of what's possible with magnets or lasers, it's focused on an approach called a sheared flow Z-pinch, and betting that by building something less capital intensive and easier to engineer, it can iterate faster and get to market sooner. Ryan Umstad, Zap's VP of Product and Partnerships, explains.
So Zap Energy, no magnets required, right? So the idea here is that the traditional approaches to fusion either require really big magnets or really big lasers. And Zap needs neither of those. I won't jump into the technical physics aspects of it just yet, but the idea that you could build something that actually has less capital cost upfront is important to what we're doing at Zap. But equally important, if not more so, is the iteration speed, right? So time is money, right? They're oftentimes interchangeable. And so if you can build something that's cheaper, you can also build it faster. And fusion is hard, right? Decades and decades of research has shown that fusion is hard, which means we're going to have to learn a lot, and we want to learn it as fast as possible. And so if we have an approach that we can, design, build, commission a device within a year, we have an opportunity to make very rapid progress. And I think that's what we're going to need to see to commercialize fusion energy.
Time is money. Zap is leaning into the fourth why now, startup speed and iteration. And the company thinks that the fast lane is right down the middle of the other approaches. Remember in the last episode when we talked about the triple product, density, temperature, and confinement time? Roughly, inertial confinement optimizes for density at the expense of time, and magnetic confinement optimizes for time at the expense of density. Derek Sutherland, a plasma physicist and fusioneer at Zap, explains how Zap plans to increase its triple product by splitting the difference.
So where Zap sits is kind of in between those extremes. We're kind of in between. We are a pulsed approach to fusion, but we're not getting to quite as high densities as inertial confinement, but we're also not getting to as long confinement times as magnetic confinement. We're splitting the difference on the triple product, so we sit right between those two. And the benefit of that is that you don't really have to go extreme in any technology direction. You don't need super intense high-tech Repco magnets. You don't need these really awesome lasers that tend to be expensive, and you keep having to make them better and better. We kind of have a very simple approach that's between those two, and we can use largely off-the-shelf technology in a very specific application that gives rise to a really commercially attractive approach to fusion.
That doesn't mean that what Zap Energy is doing is easy. They're bringing a fresh approach to one of the oldest ideas in fusion, the Z-pinch that generated false positives in the UK way back in 1952.
So the Z-pinch, I kind of consider it as the OG fusion concept. The principle is very simple. I mean, you're mainly flowing a current. If you think of a cylindrical coordinate system, if you flow an electric current in the plasma in the Z direction, it produces an azimuthal or toroidal or circular magnetic field around that cylinder that compresses it to very high densities and temperatures. That's where the Z-pinch gets its name. It depends on the direction of the current. But the problem with that is that without any other intervention, the Z-pinch plasma is unstable. And what that means is that there's be these instabilities that would crop up that would basically make the plasma terminate before you make enough energy to pay for everything you put in to make it in the first place. So in other words, it's hard to hit net gain without any intervention. So where Zap's value add here is using a new way of stabilizing the Z-pinch called sheared flow stabilization. And so a good analogy of this is basically having a cylindrical plasma, but you're flowing the plasma at different velocities as a function of radius. So you kind of think of this like a busy highway. You get stuck in the exit lane you actually wanted to go through, and there's all these fast cars going past you. You can't get into the next lane because you can't merge because of the shear flow between your exit lane and the highway. So similarly, we see experimentally and from theory that when we have enough of that shear, it stabilizes the Z pinch for very, very long durations compared to what it should be. And what that means is that you can hold that plasma around for long enough time to make enough energy out so you can pay for the energy that went into it. So it reopens the Z pinch as a path to net gain, and that's what makes ZAP unique, is the shear flow stabilization.
And how does ZAP measure progress on the path to net gain?
So technically, the main thing that you're changing in the Z pinch as you scale up performance is the amount of current, the electric current flowing in the plasma, and how hard you're pinching the plasma with that current. Simply, if you raise the current up, you produce a larger magnetic field, and then you're compressing it to a higher and higher density. It's like a piston being compressed harder and harder. And so then we can basically see the temperatures, measure the densities, and measure the confinement times. And that tells you what the triple product is. And out of that, you can derive like what's the Q. And so the Q, the scientific gain, power out versus power in, is how internally we're measuring our progress.
My role on this show is a role I was born to play, asking the dumb questions. When Derek told us that progress was a function of current, I asked him why they couldn't just turn the current all the way up and achieve Q greater than 1 today.
Yeah, it's a physics application and an engineering application thing. So it's very clear to do our scaling laws, and we predict this much current required to hit scientific break even. And indeed, that's our guiding light to get there. But actually realizing that in practice, of course, is a little bit more involved. And so the main thing that we're working on now is to raise the current in our pinch. And how we do that is we need the correct pulse power system to do that. And so without giving too many details, what we're learning is how to do that in the most efficient manner as possible. Because you take this energy from a big capacitor bank, and then you need to couple that as efficiently as you can to the plasma to do the thing that you want to make fusion. And so learning how to optimize that efficiency and actually realize the current that you need where you want it to flow. That's not as trivial as just saying we need this much current and boom, it's done. But we're definitely making a lot of progress, and we see a path, and we're continuing to go down it.
Coming into these conversations, I didn't realize that fusion was far enough along that many companies now view it as more of an engineering challenge than a physics challenge. Engineering is hard, obviously. Going from models and simulations to a working generator that produces more energy than it consumes is hard. But talking to Ryan and Derek at ZAP, you really feel that they're on a path to pulling this off. Iteration speed builds momentum, and it's cool to see companies optimizing for speed.
We have to point out here that one of the big reasons these companies are able to iterate so quickly and so often is that they're not burdened by the same regulatory regime that fission is, as Derek explained.
From a regulatory standpoint, it's much faster to iterate with fusion, primarily because you don't have all of the main concerns that comes with fission. So we're not using any special nuclear materials. There's no uranium, no thorium, no plutonium. And there's also criticality doesn't apply to fusion. It's not a nuclear chain reaction. And so you don't have as much of that issue of concern when trying to do experiments and prototypes and things like that, because it's just very, very safe.
Must be nice. David Kirtley at Helion, which also prioritizes fast iteration speeds, explained that regulation was the biggest risk to the business a few years ago, especially since the model is predicated on speed, but that the regulatory situation for fusion has landed in a good place.
Yeah, I would say regulation around fusion 3 or 4 years ago, I would say was the biggest risk for this technology that we could, because regulation at that time, it wasn't clear if fusion even who would regulate it or how, or there was no default answer. So it was possible we build working fusion generators and then can't deploy them because there isn't regulation. And not to say that the regulation is too hard or too easy, it just didn't exist. And so that was a big risk for the company, for all the companies, but also to the technology in general. And so we started working with the NRC, the Nuclear Regulatory Commission, a number of years ago. I've given a number of talks at the public meetings. We've been working with the technical staff and the commissioners over the last 3, even more years to try to figure out where does fusion fit in the regulatory landscape. And our goal was that it fits somewhere. It mattered more that we fit in the regulations as is and didn't need new ones more than it mattered, exactly where we fit in those regulations. So they announced the NRC commissioners voted unanimously earlier this year to that fusion be regulated under what is called Part 30, which is the particle accelerator and hospital parts of the regulatory code for nuclear. What that really means for us is that we're regulated by the state. So the state in Washington, the Department of Health, regulates us rather than a federal body. And that's really good for Helion because we've been working with them since 2018. So our previous systems have all been already regulated and licensed, inspected, all of those things. Because we want to make sure that fusion gets to the world quickly. That's great, but it's got to be safe. It has to be. That's an a priori requirement. And so our goal is to work, and it's really great because we've been working with the state regulator for years. And now we have the job of taking not just Washington, but all the rest of the states and having to teach them about fusion. And so we're working with the state regulators, all the agreement states, on how to actually regulate fusion and what it means and what's easy about it, what's hard about it, and how to do it safely.
Move fast and safely. We talked a lot about how regulation slows down construction projects when we talked about nuclear fission, and that the regulatory burden is a big reason that nuclear plants end up being so expensive. But we also discussed the negative impact that regulation has on iteration speed and ultimately safety. By making it harder to test and iterate, regulators impede the development of safer nuclear reactors. That needs to change. Fortunately, it seems as if fusion won't hit the same roadblocks, and Helion is taking advantage of the opportunity to test and iterate quickly. David told us that the secret to the company's speed is that it engineers systems that are easy to make in order to get on the grid as soon as possible.
A lot of us at Helion came out of some of the scientific and academic programs where we were focused on discovering physics and doing new diagnostics and learning what we could about fusion, but not delivering a product. When we spun off Helion, our goal was make electricity on the grid as soon as possible. Even if sometimes it's not as fun, even if sometimes it's not as elegant, what shortcuts can you make to move faster? And so things we really do, and that's part of been the mantra of Helion, is how do we iterate really quickly? We're building our 7th prototype for Helion. How do we actually get electrons demonstrated and on the grid as fast as possible and engineer systems that are easy to make? And so that has been the mantra as we've built all of these prototypes over the years.
Helion's approach is not without its detractors. Its 2028 target date with Microsoft is wildly aggressive. Some in the industry see Helion as a manifestation of Silicon Valley bravado, but believe that in fusion, you can't just move fast and iterate your way to success. So we asked him what he thinks the company's doubters miss.
A lot of it comes back to looking at how modern hardware technology companies operate. Actually, it's less on the physics and more on how are you building a company. Think about the SpaceXs and the Teslas of the world and many others, but a lot of the modern aerospace is a good example of can you build and test as fast as possible and iterate. And while in January, we were running our 6th generation system while physically building the 7th generation system and engineering the 8th generation system and doing that all at the same time. That's how you speed up the process. And so our first peer-reviewed, published, we did lots of thermonuclear fusion happened in 2011 on a small-scale system funded by the Department of Energy. And since then, we've now built 4 more systems, iterating on that, increasing the yield, increasing the neutron output, increasing the fusion reaction rate. Published about a year ago that we had been the first ones to do deuterium and helium-3 fusion at all. In bulk fusion, we were the first ones to do that, we think, ever. And then also that we were the first private company to hit 100 million degrees, that operating temperature for fusion, that key temperature. And so we've set those milestones and those metrics all along. But a lot of that comes back to the philosophy of how can you build fast? Is that diagnostic going to take you 4 years to build? Well, it's too long. We're not going to build that diagnostic, even though it's the best one. Is there a cheaper diagnostic that's faster that I can build in 6 months? That's the one I'm going to pick. And we keep that at every stage, even though sometimes it's hard. Sometimes it's a bit chaotic to have all of those parallel things happening all at once.
Julia, you've got to be proud as a SpaceX alum. The company came up a lot when we talked to fission companies, and here it is again as part of a why now and how so fast for fusion.
I think the reason it keeps coming up again and again is that while fission reactors and fusion generators are both among the hardest machines in the world to build, so are reusable rockets. And what SpaceX showed is that rapid experimentation and iteration times don't just apply to software or simple hardware. A machine is a machine is a machine, granted, perhaps with more complexity and more pieces to it, but the same tight feedback loops should benefit all of them.
It makes sense when you take a step back. Go fast to go fast. Make mistakes, learn, iterate. That doesn't mean that what Helion is doing is easy, though. It's doing a few things that are really, really hard, all rolled into one.
First, it's using magneto-inertial confinement fusion, a hybrid of magnetic confinement and inertial confinement.
The goal is to take the best of magnetic confinement, which is that keeps that 100 million degree fuel from touching the wall, because you don't want that hot fuel to ever touch the wall. And the best of inertial confinement, which is don't hold on to it forever. Nature is unstable and doesn't like that. Instead, squeeze it and get to fusion as fast as possible. And then adds that third one that most people aren't doing, which is directly extract that electricity. The trade-off of it is, the big trade-off is that all this has to happen fast. So it's all pulsed. That's the inertial part. The beauty is you get to do it fast. The trade-off is you have to, which means now you need triggering systems that respond in nanoseconds, in billionths of a second. Technology didn't exist 10 or 20 years ago. And you need massive pulse power systems, big high voltage electronics. And so that's the big trade-off there. So we have to design and run these big power electronics. In some way, Helion is more an electronics company than it is a fusion company. And that's where a lot of our technology and our team focus on, is those big power electronics.
Then there's the fuel. Helion is using helium-3, an element that I learned is common on the moon by watching For All Mankind, but one that is not common at all here on Earth.
I love For All Mankind. I do say that if you need to start your business by going to the moon, you probably have a rough business model ahead of you and a rough road ahead of you, as maybe was seen in the TV show. But for Helion, in fact, what we named the company after, the nucleus of a helium-3 is called a Helion. The helium-3 fuel is one of the older fuels, actually. And the brilliant scientists that did a lot of the early work in fusion recognized helium-3 would be a really great fuel, because you take a deuterium and a helium-3, and when you fuse it, it forms a helium-4, regular old balloon helium, and a proton, but all charged particles, all electricity, all trapped in the magnetic field. Two challenges. One, just like you pointed out, there isn't a lot of helium-3 on Earth. So how are you going to even get helium-3 to test it? And then how are you going to generate it in your system? And the other is that it requires higher temperatures to operate. So both of those are two negatives that you have to overcome. The first one we solved with, we patented this, but we solved this by essentially the high efficiency, this energy recovery. What it really lets you do is do fusion a lot cheaper. And this is the thing that we got really excited about. You take two deuteriums, not a deuterium and a helium-3, but two deuterium atoms, two deuterons they're called. You fuse them together and they make helium-3 in gas form. So if you have fusion already, then you can make helium-3 to do helium-3 fusion. But the key to that, unlocking that, is having really efficient fusion and really efficiently putting electricity in and recovering it out. And if you're not doing that process, it's hard to make helium-3. And then it's hard to burn the helium-3 to make electricity. And so it was a little chicken and egg problem that required modern high-speed transistors and fiber optics to unlock that.
And finally, it's doing fusion in a way that can directly harness the electricity. Remember in episode 7 when Casey Hanmer told us that nuclear reactors were stuck in the Stone Age? No? Okay, we'll play it again because it's a great clip.
At the end of the day, if you are boiling water to make energy, you can make heat however you want. You can make it with nuclear power, you can make it with coal, you can make it with gas. But at the end of the day, you're still boiling water. It's like Stone Age, like make water hot, boil water, turn turbine, right?
Turns out most fusion generators do something similar. David and Helion are trying to skip that step and just capture the electricity from the source, which is only now possible because of all sorts of technological advances.
We've done fusion a long time, and our goal is to do fusion in a way that's different than other people. Our goal is to take lightweight isotopes of hydrogen and helium, fuse them together under intense pressure, and form heavier atoms and release a tremendous amount of energy. But we don't want to release heat energy, we want electricity. And so our goal is to do fusion in a way where we can directly harness the electricity from that fusion reaction as electrons and get it out on the grid as soon as possible. So there's a whole bunch that goes into there. Our systems are pulsed and electromagnetic, but really always the focus is how do we get electricity out of fusion as fast and efficiently as possible. It takes a level of technology before it actually can happen. So this is something I think about a lot, in that the first cars were electric cars. In the 1800s, there were these electric cars in New York. They were a commercial product. But the batteries didn't exist, the motors didn't exist, the transistor didn't yet exist. And so they couldn't actually make that small niche product into a widespread car. Then gasoline engines took over, and we had 100 years of gasoline engines. And we're only now at the place where we have the power electronics that are efficient. We have regenerative braking, we have lithium batteries. Finally, now the electric car makes sense. And so if I was doing fusion in the 1950s, I'd be doing thermal fusion too. I'd be using the energy conversion that we could do then, even though fusion makes charged particles and electrons already, but I'd be using those technologies. So it's taken modern high voltage power electronics, fiber optics, gigahertz speed computing before we can really do fusion in the way that harnesses the electricity directly.
I know that I'm getting a little bit cheesy on this episode, and I've written about this idea before, but there's something magical to me about the fact that these disparate branches on the tech tree, high voltage power electronics, fiber optics, gigahertz speed computing, machine learning, magnets, all of that, all developed for completely non-fusion related reasons, all turn out to be critical to making fusion happen, and potentially to making fusion happen just in time to be a serious weapon in the fight against climate change. There's this physical phenomenon, two light atoms fusing together to produce a heavier atom and a lot of energy, that occurs naturally in the sun, that physicists figured out about 80 years ago, and that researchers have been working on over those past 8 decades, that startups may now finally be able to do in an energy profitable way because of all of these other seemingly random developments. I'm not a religious man, but at the very least, capitalism works in mysterious ways.
Amen. And as we've discussed throughout this season, for an energy source, no matter how magical, to work in the capitalist system, it's got to compete by doing something that no other energy source can, or by being cheaper than the alternative. Fusion generators will live inside of power plants. Companies need to convert the energy from the reaction into electricity, which they can sell directly to customers or into the grid. And while it's early, none of these companies have yet achieved Q greater than 1. These aren't just research projects. These startups have had to design their companies with unit economics in mind. So we asked them to describe what the unit economics of a fusion plant might look like. JC at Fuse told us that he looks at 3 different variables.
So I'll preface this by saying different fusion concepts may have slightly different way to think about it. But in my mind, there's like 3 variables, right? The first variable is how much does it cost you to create the fusion conditions, right? Which is like the dollars per joule delivered on the target. How much does it cost you? Like NEF, for example, they have this 400 megajoule laser, and then they deposit roughly 2 megajoule to the target, right? And like, what's the cost of the laser? It's like a few $1 billion. And so their cost per joule delivered on target is roughly like $2,000 roughly dollars per joule delivered on target. So that's the first function that I look at. And how can you minimize that dollar per joule delivered? And so we think Fuse can get at some point to $40 per joule and even lower. The second variable is you've delivered this much energy to the target. Now, how much can you produce, or to the plasma? And how much can you produce? That I think is a more, engineering function. So it's like the more efficient this reaction becomes, the more energy you get, which will decrease your cost, because you have the same cost, you just can get more power. And if you think about NEF, they haven't upgraded their laser. So it's the same laser that they've built that over 10 years, they've increased the efficiency of the target by 1000x. And it's the same laser. They just improved like the target design and engineering and physics, and they've improved the efficiency by 1000x. Then the third variable is how much does it cost you to take the fusion output and turn it into electricity, which I think this is more predictable because there's essentially looking at fusion as a heat source and converting a heat source into electricity. Unless you're doing direct electricity conversion, which I think there's not much precedent. So I can talk about that. But in our case, these are the 3 functions that we think about. Dollar per joule delivered to the target, and then like how much is the fusion gain, And then what's the cost to convert the fusion gain into electricity, which is more predictable? And so Fuse is focusing like intensely on just decreasing the dollar per joule delivered to the target. And then obviously improving the efficiency.
JC lists 3 factors. 1, how expensive is it to deliver the energy to the target? 2, what's the fusion gain or Q once you do? And 3, how efficiently can you convert that fusion gain into electricity? It's kind of a bottoms-up approach. Ryan at Zap Energy explained how they think about unit economics from the top down, using overnight capital costs. Overnight capital costs are the hypothetical costs if the projects were completed overnight, and is often used in large infrastructure projects to normalize for the impact of time, including removing things like inflation and interest payments.
Yeah, and I'll caveat these with no one's yet built a commercial fusion plant, right? And so we're all doing our best to estimate the costs. And so we're doing things like, class 4, class 5 estimates. That's a terminology from the Association for Cost Estimating of, different ways to price out what you think your nth of a kind commercial unit might be versus what you think your pilot plant might be. So as we've gone through that with Zap, we started to see overnight capital costs in the range of something like $3,000 to $4,000 per kilowatt. What does that mean? Well, that's about half the overnight capital cost of advanced nuclear today or of solar thermal, but it's still significantly more than one would pay for like a natural gas turbine, which might be closer to $1,000 to $1,500 per kilowatt of overnight capital cost. What that leads to is a power plant that you've spent money up front to build, but now your operations and maintenance are quite affordable, right? Our fuel costs are practically negligible, right? When it comes to a fusion power plant, fusion is such an energy-dense fuel that you measure the annual input of fuel in kilograms, not in train cars, right? And so I can kind of ignore the fuel costs when it comes to operations and maintenance. But that leads me to levelized costs of electricity that are in the range of something like $30 to $60 per megawatt hour in terms of our estimates today based upon different kind of input assumptions that we can make. So that makes me competitive. It's not the cheapest electricity source today. But again, what I think the market's going to be in drastic need of as we look towards the 2030s and beyond is an on-demand carbon-free source, right? And renewables just don't get us there by themselves. And so I'm comfortable that a $30 to $60 per megawatt hour is a competitive LCOE for what the market will need in that time frame.
Francesco at Proxima points out that while being cost competitive is important, and the company's model suggests that it can be, getting it to be cheap enough works out in the short term because fusion energy is so compelling and versatile.
Yeah, the cost of energy that can come up of fusion is, of course, uncertain. What our system analysis says is that this could be cheap. That is not a statement to say that it has to be cheap. Fusion is so compelling that if you get it done as a safe, abundant, clean source of electricity, process heat, possibly making hydrogen, you think about all the possibilities, then it doesn't really have to be the cheapest thing. We don't have to make it cheaper than photovoltaics today. We're not competing for that kind of market. So if you get to a power plant that makes order of a gigawatt with $3 billion, then you're in business. What you really want to look at is not actually the overnight cost of a new power plant. It's rather the levelized cost of electricity, this LCOE, as it's called. The models tell us that we can achieve 5 cents per kilowatt hour electric, which will be extremely compelling. If we manage to be anywhere in that order of magnitude, that's great.
Ian Hogarth of Plural, Proxima's co-lead investor, added that thinking of fusion in a vacuum undersells its strategic importance and the role that governments will play in supporting its initial growth.
It's just that it's such a deeply strategic technology. There's going to be a race for fusion power globally in the 2030s where people are going to try to, have fusion connect to the grid faster in their country than other countries because it's going to be a massive new industry. It's going to be, it's going to underpin a lot of progress and a lot of opportunities. And so I think you're going to have very significant subsidies emerge in the first chapter of kind of getting fusion on the grid. If you're thinking like a state or seeing like a state, you're sort of thinking, how much would I pay to get the world's fusion industry to be based in my country? You probably pay quite a bit because it's actually going to be pretty strategic in lots of ways. And so I think I think there's going to be some very significant state involvement in fusion in the early days, as there has been up until now with the likes of Max Planck and the Penrose 7X. And I think there may also be a role that some of the largest technology companies in the world will play, like the offtake agreement that Microsoft has agreed with Helion, which I think this question of kind of, AI requiring more and more energy and fusion as a kind of baseload source of energy that doesn't have some of the downsides of fission is going to sort of move up the agenda of large corporations as well.
That point that Ian just made is a good one. We're going to need a lot more energy, thanks in large part to companies like Microsoft that are building power-hungry data centers to support the growing demand for AI. Clea at Lower Carbon said that estimates of 5x electricity demand in the US by 2050 are probably conservative.
Ultimately, the demand for electricity in the US alone is going to grow at least 5x by 2050. And I'm pretty sure that's insanely conservative, because when you look at computing demand alone, you need about 10 years for that to be effectively the same demand of the entire US from an electricity standpoint. So we're set up for a lot of electricity demand. And enter fusion. Don't really know exactly where that's going to be in 2050, but right now we're really excited about a lot of technologies that are going down the learning curve and could represent a really significant piece of that energy pie in 2050. And a lot of those projected to be, sub $70 per megawatt hour. And that's really, really valuable in terms of a firm source of electricity. Some might project that somewhere between 10 to 30% of the overall energy source pie.
Make no mistake, though. Ultimately, the goal of fusion is to come down the learning curve to the point where fusion can replace fossil fuels globally, whether that happens by 2050 or sometime later. That's going to mean rolling out fusion plants across the globe. We asked David at Helion what he thinks the rollout will look like once they demonstrate Q greater than 1, and he was clear about the goal.
In the world, there's over 4,000 gigawatts of installed fossil fuel capacity out there. And our goal is to replace it all. And I don't think one type of fusion probably is enough to do all that. We're going to try. We're going to move as fast as we can. But I think that you're going to have different kinds of power in different locations, and you're going to need those, whether it's remote, whether it's military bases, whether it's giant factories, whether it's data centers, and they're going to require different kinds of power. And so our plan is, yes, we demonstrate electrons on the grid in 2028, and then we have to scale and manufacturing as fast as possible and start manufacturing these systems to deploy them. And so we're going to do that as fast as possible. Our goal is to get to, by 2030, we're now making generators, and we're making generators per day rather than generators every few years. That's a big scale. That's a big lift. And so as a human, I want other fusion and other types of advanced carbon-free power out there in the world too, because we just have that big of a need, and we need to move that fast. So that's my view. We're going to move as fast as we can, though, and we engineer that into the systems. Behind me here in Everett, Washington, we engineer the mass manufacturing into the systems right now.
And because Helion plans to directly convert the fusion reaction into energy, cutting out that third leg of the cost structure that JC mentioned, it believes that it can make fusion really, really cheap. So cheap that it can compete directly with all of the other energy sources and win. We asked him what the world looks like when that happens, when we have abundant fusion energy, and this is what he told us.
The whole team thinks about this a lot, that we believe we have an approach to fusion that can be low cost and generate electricity at a cent a kilowatt hour. Eventually, we want to get there. Right? That's radically low cost. And what that means is that we can go out and replace fossil fuels. We can go out and stop climate change eventually. But what it also opens up new things. We're looking at, there's many parts of the world that don't have the amount of low cost electricity we do. And so the standard of living throughout the world in India and Africa and Asia, like those are the markets we really want to address. And then the big ones, like our first customer, is data centers. We're seeing AI growing at an enormous rate, and it's going to need power. And our data center and computer infrastructure is going to require massive amounts of power, and we want to be able to support that. We want to be able to support that world. And so that's what we look towards, and we look towards what that world could look like when you have massive computing available for everyone in their pocket at home, and can we help support that?
I think that's why we're all in this, and why using atoms to generate clean energy is worth doing, even though it's so hard. We can stop climate change, open up new use cases, and bring energy to parts of the world that don't have access to it. I think it's one of the most important projects humanity can undertake.
It is not going to be easy. Every person in Fusion that we spoke to pointed to challenges and risks that their companies face, and they're non-trivial. Achieving Q greater than 1 and eventually Q infinity is one of the biggest challenges humanity has ever undertaken. We don't mean to gloss over those challenges, and we'll release full episodes with some of the founders so that you can hear more of the details from them. But I think the world's assumption is that fusion energy is practically impossible and impossibly far away. And we wanted to do this episode to show you that it's simply not true anymore. I kind of got fusion pilled when I wrote The Fusion Race in May. But Julia, I'd love to hear how your thoughts on fusion have changed after having these conversations.
I thought fusion was essentially a science project before we started working on this together. And, fission was the area I kind of knew and understood and was like, hey, we do these today. We have maybe a go-to-market problem right now with expanding where the footprint is for fission. But it's so cool to see that there has been incremental progress being made with fusion. We've achieved Q greater than 1, albeit for short periods of time, and we're making progress. We have all these different approaches too, and I actually really like the analogy of the fission reactors to the fusion reactors, because it kind of helps you say like, okay, we're doing this thing where we split atoms over here, we're merging atoms over here, and there's a few different ways you can go about setting up your generator or your reactor to do that. So that's kind of fun. It just helps you kind of understand the problem, understand that there can be these different approaches to it that each come with their sets of pros and cons and risks versus benefits. And it's been fun. It's just like, as you put it, Packy, to kick this whole thing off, we're in this race. We have these different approaches with these different companies. And now it's just to say, like, let's see who can iterate and learn and improve the fastest and be the first people to actually get there with more consistent Q greater than 1, and then ultimately something that's commercially viable.
Yeah, I think very well said. That was one of the things that blew my mind, I think. And one of the things that made me want to write about fusion and even do fusion in this season in the first place was that with so many companies approaching this and really, really smart people, and each company that we talk to, I think has a real shot. But with so many approaching it, somebody's going to figure this out at this point. One, because there are so many approaches, but two, because they are all seeing this kind of why now. And that's why they're entering the space. I do think the why now moment for fusion actually makes a lot of sense. I think even after writing that piece, one of the things that surprised me having these conversations is really how much of an engineering challenge it's become at this point, as opposed to we're discovering new physics. The physics scene kind of known, and it's yeah, we've known about this stuff for 80 years. And now we have the software where we can actually design the thing that makes sense, or we can make the right engineering trade-offs, or we've seen SpaceX, or we know this is possible now, so let's go do it. I think my biggest surprise maybe coming in was, when I wrote that piece, I kicked it off by writing about Helion's deal with Microsoft. And I think a lot of people are like, Helion's not going to pull that off. That's just a Sam Altman, Silicon Valley thing. After talking to David, I would bet my own money on Helion pulling off, commercial fusion before 2030. It sounds ridiculously aggressive, but they've been doing this since 2013, and they have they're on their 8th generation of generator.
Yeah, I was going to say, I love how fast they're moving. I love how he talked about, they're always working on 3 at one time, right? One that's actually being tested, one that's, coming out of design and in, final specs, and they're about to start testing, and the other one that they're designing in the future, and they're all impacting each other, right? What they're learning today on, version 6 is influencing the tweaks on version 7 before that gets tested, which goes into how they're designing the 8th prototype. So I love that. I love that process. It's gotten me thinking. Fission and fusion obviously are different, and they are different in their life cycles in terms of where they are in development. But they're actually not as often grouped together as you might think. Why is there no just atomic energy category where we're hey, we discovered renewables, they're pretty awesome in all these ways, but here's the future. It's the potential of the atom, right? Whether you're splitting it, you're fusing it. This is an awesome category. Why are people not just atoms for peace, whatever it is? We love this. Yeah. We love this category of thing. I mean, maybe it also, we've talked a little bit about rebranding this whole topic. Does that need a little bit of is there a branding opportunity here?
Yeah, I mean, we talked to people about this a little bit, but I think to me, it seems like the fusion people are kind of give us the clean sheet of paper. We are being regulated by the health people, and it's way easier over here. Do not lump us in with fission. We actually love fission, and we think it's great and we want more of it. But for our regulatory path, like we really want to have our own kind of
They don't want to be
way.
lumped in with the baggage of fission. It's true. And I get it. I really get it. And I'm actually very happy that fusion has seemed to have found something that's not so burdensome, the way that fission is just really bogged down.
One of the things that's come up, and I'd love your thoughts on this, as we've had these conversations, is like, obviously fission has all of this momentum right now. I feel like maybe one of the biggest risks from like getting change to actually happen, because it does take so long, is that like, let's say Helion, hits the grid in 2030. This momentum that we have with fission, maybe people are like, all right, whatever, we'll just go with fusion now. Does that worry you at all? Or like, what are your thoughts on that? Because I can see like a lot of this momentum that fission has. Maybe people are like, all right, we just wanted atoms. Like we got atoms, great.
I mean, if we truly can get there that quickly and then scale up, that's the other question, is like, how quickly can you roll this out commercially? I mean, great. Like, it's all atomic. It has these wonderful benefits to it, extremely energy dense, extremely low carbon footprint, and reliable, right? The things that we don't have the intermittency of renewables. It's all great. Both fission and fusion have those qualities of energy that we think are so appealing. And so either one, honestly, like, whatever's going to work best, like let's do it. I'm still a believer. I think we both talked about this in like having a diversity of energy sources in case, your supply chain sucks and one of them you can lean on another, and, you get strength through diversity like that. So it's probably good to have both. And listen, we know how good these fission reactors are. I mean, they've been around 40, 60 years now. They're now starting to license them for 80 years. Like, no question they're going to stick around, especially now that we have seen public attitudes changing. And so I think, I don't think fission is really going anywhere, but it is a good question of like, how much are we really going to see it expand? And what's that race look like in terms of timing between fission and fusion?
Yeah, I mean, I am fully nuke pilled after the season. Coming into the season, I was already pretty nuke pilled, and now fully nuke pilled. I think like in reality, we should be building fission reactors for the next like 50 years, 100 years, whatever that number ends up being. The thing that worries me is like maybe you get caught in this in-between spot where fusion actually hasn't proven that it can like scale up, but it actually seems so close that people are like, that maybe fission loses some of that like popular support momentum. And then we get stuck in between where we don't change the regulations on the fission side, but fusion actually hasn't figured out how to scale up yet. And like, that puts us in a weird spot. Yeah. That would be the biggest risk that I can see.
I think it's a big risk. And I think it's actually important that you do still have the two cohorts, fission camp, fusion camp, that are just really championing what needs to happen for their specific field to push the ball forward. And like, we just need to be pushing for it on all fronts, right?
Yeah. Yeah. I mean, I don't know. I came out of this whole thing, and we'll talk about what the future looks like in the next episode, but like really thinking that there is a clear path on both sides, fission and fusion, atomic energy together, to like actually putting just a shitload of energy on the map that's clean, that is essentially limitless. Like if we can do this, if we can like not get in our own way, the world is going to be a much different and I think better place if we pull it off. So
100%, Beck. Yeah, I think we know what we need to do in both categories. And fortunately, there's just a bunch of awesome startups and others who are working on, again, pushing the ball down the field on both. So super exciting times.
Amen. So on the next episode, and sadly, the last episode of season 1 of Age of Miracles, we'll look to the future and we'll discuss what the world might look like if everything goes just right, if we have cheap, abundant energy for all.
I'm so excited for our final episode. It's going to be sad to wrap up the season with you, Packy, but I think this last one's going to be a great one. And it's been so fun to have taken the time to dive into fusion today.
See you next week.
See you next week.
Thank you for listening and watching to this episode of Age of Miracles. If you like what you hear, please rate, subscribe, and share. And if you're feeling really generous, tell us what you think in the comments. Plus, we have a ton of resources and references in our resource hub if you want to go deeper. And we've linked them all in the show notes below. See you next week.